Welcome back to the 5th video of the series. Today we are going to do some programming and use our LCD as a debugging tool. Do you remember my test program from the end of the last video? It was messy and really bad for a multiple number of reasons. The first thing that strikes you when you look at it is the repeating pattern of this delay loop code between the instructions sending commands and data to the LCD. Anyone with even basic understanding of programming knows that such a repeating piece of code implementing a task or an operation should be extracted to a function. Also, for someone not familiar with the text LCD we used, the code sending, for example, a 01 hex to IO port 0 says completely nothing. If they saw a call to the text LCD clear display function instead, they would understand much more about the code they look at. As you can see, there is plenty we can do with such a simple test code to improve it. Let's start with a delay loop. Let's assume that all of the delay loops in the program use the same number of iterations for simplicity. It is trivial to wrap it with a label in front, let's call it simply delay, and the ret instruction on the back. Then we just need to replace all the occurrences with the call delay, right? Yes, in this particular program it would work indeed. But let's imagine now that we want to display a sequence of characters on our LCD, for example like this. It sends the string to our text LCD data IO port, character by character in a loop. As usual, the CX counts the number of characters to send. Now we just need to add the call to our delay function. Simple. Well, it's not. If you look carefully, you'll see that each call to the delay function destroys the value currently held in the CX register because the function itself uses it in its own loop. Well, one may say, you just need to add a comment for the user to save their CX on the stack before calling this function. Or, even better, we can push the CX at the beginning of the function and pop it back at the end ourselves, making things easier for the caller. Both solutions have their drawbacks. The former one requires the caller to add this push-pop sequence every time. If they forget, the program fails. Also, there is a good chance that the function may be used in a high-level language like C. How do we tell the C compiler to save their CX register before calling this function? The latter solution is slightly better, as the call to the function doesn't change the value of any registers, but it is slower because of the push and pop instructions always being executed, even when the caller doesn't care about preserving the CX value. There must be some kind of set of rules to be followed by both sides, the caller and the callee. And in fact, there always is. It is called a calling convention. Calling conventions are mainly dictated by the processor architecture, then, on top of that, some additional rules may be imposed by the operating system and the high-level languages. They define which CPU registers have to be preserved by functions and which don't. The latter are called scratch registers. Also, which I haven't mentioned yet for simplicity, they define how the parameters of the functions are passed over and how the results are returned back to the caller. In the 16-bit x86 platform, which we use here, only the SI, DI and BP registers need to be preserved, all others are scratch. Functions always return the result in the AX for data up to 16-bit, or in the pair of the DX and AX if the return data is 32-bit wide. The parameters in general are passed to a function on the stack. That means that the caller pushes all the parameters to the stack prior to invoking the function. Details about how that happens differ between the languages. Let's have a look at the two most popular calling conventions, the C one and the Pascal one. The differences come from the fact that C allows passing a variable number of parameters to functions, while Pascal allows only a specific declared number of parameters. When you call a Pascal function, the first argument to be pushed is the first one declared, so they go to stack from left to right. Since the function knows exactly how many parameters were pushed to the stack, it uses a special version of the ret instruction in x86, which takes a number of bytes to pop from the stack at the end and before returning to the caller. The C function, in contrast, cannot do that because it doesn't know how many parameters were pushed to the stack. Therefore, it is up to the caller to pop them after the call. Additionally, for the same reason, the parameters are pushed in the opposite order starting from the last, so the first one is always on top of the stack, having been pushed last, so the function can always find the arguments in the same relative place. To summarize, the Pascal function has its parameters pushed to the stack from left to right, and the callee removes them at the end. The C function must have its argument pushed from right to left, and the caller is responsible for removing them from the stack afterwards. Microsoft created a variant of the Pascal convention called standard call or std call. The difference is that the order of parameters is the same as in the C one. It was and still is widely used in both 16-bit and 32-bit Windows, where all the API functions comply with this calling convention. As a side note, these calling conventions were later almost exactly translated to the 32-bit world of x86. The beginning and the end of each function, usually called the prologue and the epilogue respectively, preserve the stack pointer, the SP, and use the other stack-related register, the BP, for setting up something called a stack frame of the function. It is the area of the stack where all data related to this function reside. The function may access them using the BP together with an offset by pointing to the parameters of the function or local variables declared within the function, which sit on the stack as well. Obviously, for the prologue and the epilogue to work, the function may never change the value of the BP register. As a summary of everything we've said so far, let's look at this example function, which searches the given string for the first occurrence of the space character and returns the offset at which it's been found, or -1 if it hasn't. So let's start from the beginning of the function. As you can see, this is the label which defines the beginning of the function. Semicolons start comments in this assembler. So let's start with these first two instructions. This is the so-called prologue. The first one pushes the current value of the BP on the stack, and then it saves the current SP into the BP. So we can then access the stack, as you can see, using the BP register. But we can't change it inside our function because everything would break then. And that's the prologue. You usually will see this in front of every function in C convention. Now let's go down to the bottom of the function. Just before returning from it, we've got these two instructions. We just undo what the prologue did. So we reset the SP with the value of the BP and then pop BP back from the stack. So that's the epilogue. Now what are we doing here? We just decrement SP by 2, which means that we kind of reserve a 2-byte space on the stack for local variables. We don't really need in this function any local variables, but just for completeness of this example, I decided to add it in. We can access parameters on the stack using BP and some offset. And as you remember, the first parameter, which is the address of the string we are searching for a space, is at the offset of 4 bytes from the current value of BP. That's what we're doing here. So we are pointing to the address passed as a first parameter to this function. The second parameter is 2 bytes further away from the current value of BP, so we need to use offset of 6 bytes. That's the length of the string. And that's what I was talking about just a minute ago. That's the negative offset, which means that this value is our local variable, which we reserved by decrementing the SP by 2 at the front. As an example here, we're just saving the DI, which is the pointer to our string, into this local variable, and then we go down to the actual function. Let's quickly look how we call this function. Let's go up before calling the actual function here. We need to push our 2 parameters of this function onto the stack. First one is just the length, which is calculated by subtracting the beginning address of the string from the label which marks the end of the string. So the difference is the length of the string, and we push this value using the AX register. Then the first parameter, remember in the C convention, we push parameters from the last to the first, so from the right hand side to the left hand side. We push the length here, and the beginning of the string we just load into AX and push this value just before calling find space. Well, this code really ignores the return value. It was just to present the example of C convention written in assembly, but the last thing we have to do, whether we ignore the return value or not, is to remove those two values pushed before the call find space from the stack. We can do this by popping twice, but that would be longer and we don't care about the values at all. So the simpler thing is just to add 4 to the current value of SP, which just moves the stack pointer by 2 16-bit values. From now on, we will use the C convention, as I'm planning to mix the assembler with C in due course, so it seems an obvious choice. Finally, we can fix our delay function by applying the C calling convention. Also, we can now add a parameter to it, which specifies how many iterations it would do. So here it is, our delay function now changed to receive one parameter, which defines number of iterations inside the loop. We already recognize the prologue and the epilogue. The actual body of the function is really simple, just 3 instructions. As you can see, we first load the CX with the value from the stack. BP plus 4 means we are accessing the first and only, in this case, parameter of the function, and we load the value from this parameter. We load it to the CX register, then we decrement it, and if it's not 0, we loop back until the CX gets down to 0. So it's exactly the same code as we had before. Now we just added this parameter, which we can then change in each call to this function. This is our C declaration for the function. We can as well, of course, use it in our C code, which we will later do. Let's now take care about the communication with the LCD. As you probably remember, sending a command to it is as simple as writing a byte to the I/O port. In such cases, we can simplify the function's code. That's because the function doesn't take any parameters and, what's also important, doesn't call any other functions from itself. As we never have to access the stack or modify any registers which need to be preserved, we can simply omit the prologue and the epilogue. This kind of a function is called a leaf function. The analogy to a tree is quite obvious. Normal functions branch off into another, like tree branches do, down to the leaves, which are at the bottom of the hierarchy. Sometimes, when the function is simple and doesn't need to use the BX register for anything else, you may see this kind of simplified version of the prologue. Since the BX is a scratch, you can use it to access the data on the stack, instead of pushing and popping the BP, saving a few cycles. If you look at all of the code in this file, you'll see all of the function types I mentioned here. Please see the video description for the link to the code. Now, before we dive into C programming properly, let me show you and explain the code I wrote to initialize the CPU after the reset. The first part is exactly the same as before, with one exception. Instead of just hard coding the value for the stack segment, and the file is here, so we define this constant with this value of 7000 as before. I also defined our I/O port of the text LCD. As you remember, the command one is 00 and the data one is 01. We can use those labels throughout our code instead of just hard coding values. And as you can see, I already prepared some comments for the next device we will attach to our computer in the next video. But for now, let's go back to our init procedure. So we, apart from initializing this stack segment register and our ES as well, we also need to do a few things before we can correctly use a C language in our program. That's because when we define some data, they need to be accessed via the data segment register, and the compiler puts them into a separate region of our flash memory, and with the help of so-called linker script, which is attached to this program, the compiler defines some values which are accessed via these. And for example, data offset defines the pointer in the flash where the data segment starts. The L data, it's the length of all the data already declared in our program. So what this piece of our code does, it simply initializes the SI with the beginning of the data, and the CX holds the length of the data. So what we do effectively is that we are copying all the data declared in our program into the RAM where it can be accessed by the DS and ES registers. And also, C compiler defines a special section of the data called BSS, and this area of memory holds all the declarations and all the variables which need to be initialized with 0, so they need to be zeroed out prior to executing our program. So what we do here is we just set AX to 0, and then we just store the 0 across all the data which needs to be initialized, which are defined by the compiler in this BSS section of our memory. And finally, we can initialize the values of our segment register, the DS and ES, to match whatever is currently in the SS register. So all the data in our program and the stack are held in the same segment, 64 kilobytes of memory. And then after that, we finally can call our main function. Let's now use the code we just created to drive our text LCD and write a simple Hello World program, mixing the assembler with some C code. Again, all the source code and the tool I used to compile it are linked to in the description below. As you can see, we have displayed the Hello World text on our LCD using all the knowledge presented in this video so far. But it's not the end yet. I promised you to use our LCD for debugging. Let's start from implementing a function which would take a structure containing values of the CPU registers and display it on our LCD. So here I declared this display state function, which task is to display all the registers values in hexadecimal on our LCD. And as you can see, we've got this structure as the parameter of this function. And the structure is defined here. It's nothing but just a set of 16-bit values which will hold values of all the CPU registers. Now let's have a look at its definition. What we do here first is to declare our local variable, which will hold one line of the text for our LCD. Our LCD has 4 lines, 20 characters each. So I'm just gonna display it line by line. This is our text LCD send text at function, which sends whatever is in this buffer to our LCD, starting with the 00 position, which is left top corner, and then similar code just sends another line to second line of the LCD, the third line, and the fourth line here. What we do here is we are converting the binary values. So this 16-bit value we convert to a string representation containing 4 hexadecimal digits, and this function is written in assembler here. And we do this with each of the registers, with the one exception. We've got this flags to string function which converts our flags register into a string representation. We will talk about flags just in a minute, and it will be all clear for you why we have a separate function which is written here in C. Now, before we display the real values of our registers, let's just test the code we've written so far. As you can see in my main function, just after initializing the LCD, up here, I create this structure, initialize with some values, which we can then recognize on our display. And finally, we call display state with a pointer to this structure. Okay, let's see if our display state function works. We've got something on our display, and before we get into the data on the display, I would like to explain that I've added this overlaid label on the display so it helps us to read all the data. The idea is that at the top part we have descriptions for the first 2 rows of the display, and here at the bottom we've got the other 2. So for example, and you can compare it with the program here, we set our CS segment register to C5, IP to FEDC, and then we've got the pair pointing to the stack SS to 5555, SP to 5678. The BP in the second row is 8765. Our other segment registers are here, and then the SI and the DI. At the very bottom, the 4 numbers are all the general purpose registers AX, BX, CX, and DX. These are all meaningful bits in the flags register. We will talk about it in a second. Then I'll explain how we display those on this LCD. Now we can finally display our CPU state at any given moment using our display state function. But since we need to be able to call it from the assembler as well, we need to declare our CPU state C structure in assembler as well. We cannot simply include the CPU state.h file because the assembler doesn't understand the C code. Therefore, we need to declare the same structure in assembler as well, taking special care of the order and data types of all the members, so both of the versions have exactly the same layout in memory, which means that the data stored by assembler will be correctly read by the C code. This is how our structure looks like in assembler. What's important, extremely important for it to work, is that the order of all of the members, so all of these registers, need to have the same order as in the C version. And other thing is just to make sure that the size of each of the members is exactly the same as in the C version, which is quite simple because all of them are 16 bits, which in this assembler you declare by using this res W. The W means it's a word, meaning 16-bit value. Finally, we can talk about 2 interrupts we haven't mentioned yet. The first one is the interrupt number 3. It is reserved for a breakpoint, which can be raised by a special 1-byte instruction. This means that we can insert this instruction anywhere in the code where we want the interrupt to be raised. That's exactly what debuggers do to put their breakpoints into the code. So let's write a program which would set all the registers to some known values and then raise the int3, whose handler would display values of all the registers on the LCD. So this is the bottom of our initialization code. I've made some changes. First of all, I wrote a function which initializes the interrupt vectors. I'll show you this function in a minute. Also, I decided to move the LCD init function call from the main in C directly to this initialization code in assembler, because we will use our LCD in every program from now on. I actually commented out the call to the main function, because in this example there is no code in main. The only thing we do is to set our CPU registers to some recognizable values. And then we finally will raise our debug interrupt using this instruction. As you might notice, this is a one-word int3 instruction. It's the special opcode for this, which generates 1 byte debug interrupt machine code instead of the usual 2 byte for any other software interrupt. Now we need to write the interrupt handler for int3, remembering that all the registers must be preserved, so the program may correctly continue after returning from the interrupt procedure. The trick here is also to avoid accidental change of any of the register's values before it gets stored for a call to display state function. At the end of the day, we would like to display their values at the moment the processor entered the interrupt handler, not some temporary local values, right? Before we see our int3 interrupt handler, let's have a look at this function I mentioned before, that's setIntVectors. As you can see, it's not a real function in terms of C calling convention, and that's because we will not call it from the C, and we will be calling this only during initialization, so we don't care about stack frames, prologue or epilogue. What this function does is just copy this array of values down here to the bottom of the address space in the RAM. The second part of this procedure just replaces all unused, undefined here interrupt vectors with the pointer of the default handler, which is simply iret, so it's like a NOP. Just in case we make some mistakes in the program and accidentally raise an interrupt. So as you can see, the vector to our breakpoint int3 is defined from this label, debug int handler, which I defined in this file. And this function is almost like a regular C function, as you can see with prologue and epilogue, but the difference is that it's finished with the iret instruction, which returns from the interrupt instead of regular ret. But what we need to really care about in all interrupt handlers is to not to change any value of any register. That's why we added this prologue and epilogue. This saves BP as the first thing. Then it saves the SP into the BP. As you can see, the epilogue is here, so we are sure that we would not modify BP or SP in this handler. And then we need to push all the registers we use inside the function. And because it calls another C function, we need to make sure that we preserve all the values which may be modified within this function. So we need to store all scratch registers as well. It may look scary at the beginning, but that's how NASM, the assembler I use here, calculates offset to members of structures. So first of all, this, as you might recognize, this allocates a local variable of the size of that, and that's the way to tell NASM the size of your structure. So that's the name of the structure. If you follow it with _size, it automatically defines the size of the whole structure in bytes. So we reserve that number of bytes on the stack as a local variable, and then we populate with the real values of our registers. It looks complicated, but what it does is, again, BP minus a number means that we are accessing a local variable on the stack, and because we subtract the size of the structure, we point to the beginning of the structure itself on the stack here, and then we add offsets of each of the member of the structure just to point to the correct place on the stack. So reg AX, as you can see, is here, so it would probably be an offset of 02468, so that would be assembled as number 8. So the value of the AX register will get into the correct space within the CPU state structure. And we do this with all the registers. Of course, we can't copy some registers, like segment registers, directly to the memory. So we need to do this via the AX register. And interesting thing is here, we are trying to store the BP, but not the current value of the BP within this function. We would like to know the real BP value just before the interrupt was raised. And as you can see at the top of the function, we do this first thing after getting into this code. We store BP onto the stack, and we know that the stack pointer is saved onto our BP local value of BP, so we can access the value of the BP register before raising the interrupt by looking at the memory address pointed by the current BP. It looks complicated, but if you download the code and have a look yourself, you can easily, I think, find out what's happening here. The next thing is to call the display state, our function which displays all the values on the LCD, remembering that we need to push the pointer to our structure prior to call, and call display state, remembering to clear up our parameter of the function afterwards. Let's see what can we see on our display when we erase int3 interrupt. Okay, that looks quite interesting. If you notice, the address of the next instruction after the int3 in our program is at the address 0045. Our segment, CS segment, is F000. So that is correct. Our stack is in this segment. And since we pushed the accumulator at the bottom of the stack, its current pointer is FFFE. We also set the BP to for Bs, and both DS and ES are correctly set to the same value as the SS, and then the other registers we just initialized with the values shown in this program. So that looks like our int3 works perfectly well. The IP register at the moment of raising this interrupt points to the next following instruction, so it's all fine. Now I promised to explain the flags register. As you already know, there is 9 flags, and the flags which are currently set are capitalized here, so we know that the IF flag is set, the 0 flag and the parity flags are also set, and the rest are cleared. int3 is great when we want to stop executing our program in a predefined moment, but we'd also like to be able to trace it instruction by instruction or step by step. It is impractical to modify the program by inserting int3 after each instruction, and it's impossible to do that in the code compiled from C. Fortunately, Intel built in the x86 a single-step mode for debugging. In this mode, the CPU raises an interrupt after each instruction. But to turn this mode on, we need to explicitly modify the flags register, which I briefly mentioned in one of the previous videos. So this is a good moment to talk about it in a little bit more detail. The flags register is, like any other register in x86, 16-bit wide. But in this processor, only 9 bits are meaningful. Out of these 9 bits, 6 are status flags, the other 3 are control flags, which we can modify to change the CPU's behavior. Let's start from the status flags. Those are modified by most of the logical and arithmetic instructions, and their state may subsequently be used by conditional jumps. I'll show an example in a second. The first one, the CF or the carry flag, is set when there has been a carry out of or a borrow into the result of the last operation. The 0 flag is set when the result of the last instruction has been 0. The AF auxiliary flag is similar to the CF one, but it only indicates a carry or borrow between the nibbles or half bytes of the result, and is exclusively used by a special group of decimal arithmetic instructions. The SF or the sign flag is set when the most significant bit of the result is set, meaning that if the result is a signed value, it is negative. The parity flag is set when the 8-bit result has an even number of bits set. It may be used to generate and check for data parity in a communication protocol. Finally, the last status bit, the overflow flag, is set when the result of the last operation has exceeded the capacity of the destination. This flag has an optional int-o instruction available, which raises an interrupt when the flag is set. We will see how the status flag work in the next video, but today let's just quickly have a look at our delay function. Here we count the delay in the CX register, which is decremented in the loop by this decCX instruction. It is followed by the JNZ instruction, which checks the ZF flag and jumps over only when it is not set, meaning that the result of the decCX has not been 0 yet. When finally the CX gets decremented down to 0, the ZF is set and the jump is not executed and passed over, exiting the loop. Now we can talk about the 3 control flags. One of them, the IF or interrupt enable flag, we already used. As you may expect, it enables the interrupt requests. When we tested interrupts in the previous video, we used the STI instruction, which simply sets the IF flag, allowing the requests on the inter pin to be accepted. There is a matching CLI instruction, which clears the flag. The second control flag is the DF or the direction flag. It is only relevant to the string instructions, those with the rep prefix. As you may remember, those instructions implicitly update the SI and DI values. By default, they increment these registers. When we set the DF flag, they instead will decrement them. Finally, the TF or trap flag, as you may have guessed, is the one we are interested in now. Setting this bit on switches the processor into the single-step mode. Now we have all the information needed to test this in practice. In order to use the single-step interrupt, we need to make a few changes. First is to set the vector table's entry at index 1 to point to our debug int handler. Second is to actually enable the single step by setting the TF flag in the flags register. There is no specific instruction to do that, like the STI for the IF flag, so we need to directly manipulate the bits in the flags register. The only way to do this is via the stack, as you can't simply do move AX flags. And finally, the last change is to temporarily add an infinite loop to our debug int handler to avoid the LCD being refreshed after each executed instruction and allow us to actually see what's on there. That's it! Now the next instruction after the pop-F should raise the single-step interrupt and display the state of our 8088 on the LCD. Let's try that. Okay, if you have a look at this program here, it looks like after pop-F, the first instruction which caused the single-step interrupt was the NOP at address 0049, and the following is the jump, the infinite loop, at address 004A, and that's what we can see here on the display. Current IP value is 004A, and all the other registers are correct as well. Nothing's on the stack, so it keeps the initial value of 7000 and 4 zeros in the SP. And another thing worth pointing out is the TF trap flag, which we set to get the single-step interrupt, which obviously, as you can see, has worked. Of course, we would like to be able to go through the program step by step continuously, as currently our CPU is hung up in an infinite loop, but we will fix this in the next video. Thank you for watching, and please don't forget to like this video and subscribe if you haven't done it yet. See you next time.